isothermal, right? The temperature is held constant. So this one is called the isothermal Joule-Thomson coefficient, and that's just the Joule-Thomson coefficient. But anyway, apart from semantics, what I see over here is that if I change the pressure, the temperature would change. Again, for an ideal gas, what would be the value of del H by del P at constant temperature for an ideal gas? It is 0. Yeah. If internal energy depends on temperature, the enthalpy also automatically depends on temperature because it's just plus PV. Now, look at this one. So, for a real gas only it will happen. I'll tell you the expression that comes out for the real gas. Let me take that first because we'll derive it later. You need to learn a bit, pick up a few more things before we can derive that. But for the real gas, I have it written somewhere. For a van der Waals gas, del H by del P at constant temperature is approximately equal to B minus 2A by RT. Reminds you of some other? No, this is the inversion temperature which you will get when you put it equal to 0. But any other temperature? Boyle's temperature, where the factor of 2 is missing, right? Okay, so they have to be related somehow. The Boyle's temperature was because of different interactions, positive and negative, repulsions and attractions. Over here also it's going to be essentially the same thing because if you calculate T inversion, that is where dH by dP at constant temperature goes to 0, that would be, right? So, what exact? Okay, and we'll see how to derive this formula. I'll not do it in class, but give you as some kind of an assignment. So, what essentially is this inversion temperature all about? It's very interesting, and it's given in your handouts. I have given you 2 of these graphs on page 5. So maybe you could look at that later. And in those graphs, if you see, there are 2 different inversion temperatures, and the inversion temperature depends on the pressure also. We just talk about the upper inversion temperature. Okay, you cannot get the lower inversion temperature from this formula. Yes, you can get only one, and we talk about the upper for the time being. And what it does say is that, look, I try to expand the gas. I reduce its pressure. Where is it? I reduce the pressure of this gas, and remember one thing, before I do anything over there, let me remind you that this is equal to minus of Cp, right, del P by del Ph. So, if I try to reduce the pressure over here, what would happen to the temperature of the gas? Would it decrease? Would it increase? Or would it stay constant? Well, it would stay constant if this fellow is equal to 0. But if I look at this, if I have a low temperature, then this second term is more dominant. If this is more dominant, this, as we remember from yesterday, is due to attractions. Right? And this, because of the volume of this gas, is due to repulsion. This is considered for repulsions, right? So the A term, if it's more dominant, then the gas would like to attract. So attraction, in other words, manifests as a lowering of temperature, a lowering of volume, or an increase in pressure. So, what I'm doing essentially is decreasing the pressure And if I am below the inversion temperature, the gas starts to attract, so its temperature drops down. Okay, so if it was above the inversion temperature, if it was high, okay, then this would dominate. And if I try to expand the gas in that case, it would repel further away. Yeah. One is that when I expand the gas, yes, it's expanded. But now it comes to a certain volume. It stays, it can't expand any further. So what is the second thing that can happen? The pressure is constant, the volume is constant. So the only thing that can change is temperature. So the temperature would then start to increase. That is, increase in temperature means your molecules are moving much faster and trying to overcome the repulsion. A decrease in temperature is that they are actually coming closer, kind of, and they are sitting at one place, so they are very happy being in the company of their partners. Okay. Great. So that was the Joule-Thomson experiment, and that is actually very useful for some kind of refrigerators known as the Linde refrigerators, which are based on exactly this principle. And the Joule-Thomson effect is also used for liquefaction of gases. Okay, so where they have these pumping and expansion and compression cycles where you can liquefy the gases. And one of these graphs over here shows you that it's not possible to liquefy helium very easily, because at room temperatures you're above the inversion temperature of helium. So no matter what you do, you'll never be able to liquefy helium. So first you have to go down to a lower temperature, which you could do by liquefying nitrogen or liquefying hydrogen. So this is what the graph says over here. Once you are at a cool enough temperature, then you can start to liquefy helium, not before that. Okay. And the last thing, which, no, I think I'm more or less done with today's lecture, except I put all these expansions over here, the isothermal expansion and the adiabatic expansion, but since you know that, we don't repeat, huh?
So, but we do use liquid hydrogen. It's very similar to helium.
Yeah, we do use liquid helium too.
But it is not possible to liquefy.
At room, no, you got me wrong. At room temperature, you cannot liquefy helium. So first you have to go down to a lower temperature. Okay. Let me try to read the temperature if it's possible from this printout. Or, since it's on the website, I could even show you. No, that's gases, sorry. I don't think I have a copy of this on my computer. It will take some time, but in the meanwhile we can discuss something more. I can stop this.